Hello and welcome to Vodcast 15.1. In our first Vodcast for Chapter 15, I will overview the geocentric and the heliocentric models of the solar system. We're going to start off Chapter 15 by doing a little time hop back to the golden age of astronomy. The early Greeks have been criticized, and rightly so, for using philosophical arguments rather than scientific data as their means of explaining natural phenomena. Most ancient Greeks held what's known as the geocentric view of the universe. And this view is best described as the quote-unquote Earth-centered view. As the ancient Greeks would tell you, Earth sits motionless at the very center of the universe, and everything else revolves around us. The closest object would be the Moon, the next closest object would be Venus, then the Sun, and then Mars. And then on the very outskirts of what to them was the observable universe, we had the celestial sphere. And the celestial sphere was a hollow, transparent sphere that all the stars were attached to. Now, although the Greeks relied primarily on philosophical arguments in explaining our place in the universe, they did use some observational data. And one of their biggest objections to any model other than the geocentric model was the fact that we couldn't feel Earth spinning. And then just to add to that, they thought that Earth was far too big and heavy to move. Well, spoiler alert, the geocentric model is flat out wrong. One thing that we know now that the Greeks would not have known is that in the Ptolemaic model, which is shown in this image, the orbit of Venus would lie between the Sun and the Earth. So if Earth were at the center of the universe, you would only see the crescent phase of Venus. And just to elaborate on that in case you're confused, just like our own moon, the planet Venus will have phases. Well, knowing what we know now about planets and moons and phases, the geocentric model simply doesn't make sense because we do see Venus in its full phase. I'd now like to consider a specific phenomenon that was very perplexing to the ancient Greeks. And this particular occurrence questioned the validity of the geocentric model. By definition, retrograde motion is the apparent reversal of direction of some of the planets in the night sky. Now, most of the time, if you go outside on a nightly basis, you'll see the planets appear to move eastward across the sky. However, on occasion, they'll slow down and then drift back in the opposite direction towards the west, and then shortly afterward continue moving in the eastward direction. And this apparent reversal of direction is noticeable because we're using the background stars as our frame of reference. Now, it doesn't make sense for a planet to be moving to the left, and then stop, and then move to the right for a little bit, and then continue moving back to the left. So the Greeks tried to explain this while keeping Earth at the center of the universe. To their credit, they got really creative and came up with a semi-plausible explanation. In order to explain retrograde motion in the framework of the geocentric model, Ptolemy used two motions for planets. The first was large orbital cycles called deferens, and the second was small cycles known as epicycles. I'd like to focus your attention to the picture at the very bottom right corner of this slide. Notice that Earth's position is at the center of the solar system and it's not moving. As a planet moves around us, it will orbit us in a circular pattern, and they called that pattern a deferent. That's the large circle that you see here. But then they added yet another smaller circle, and that's known as the epicycle. You can almost kind of think of this as a wheel attached to a wheel. So as the planet is moving around Earth in the clockwise direction in a circular path, it's simultaneously spinning a circular loop in that epicycle loop. And the result of combining these two motions is kind of a loopy path for the planet. I'd like to show you a brief video that should help you develop a visual understanding of retrograde motion. And what I really like about this video is it'll show you retrograde motion from a geocentric perspective, but it will also demonstrate retrograde motion from the sun-centered perspective, which we'll consider shortly. That video really nicely illustrated the concept of retrograde motion. But just in case you're confused as to what causes retrograde motion, I'd like to turn your attention to the picture you see in the center of the slide. And in doing so, we're going to put the Sun in its correct position at the center of our solar system. Earth has a higher orbital velocity than Mars. And to explain what that means, if you look at the 7 labeled positions for Earth, you notice that it makes about 2/3, maybe a little bit more of a full circle. Whereas for the 7th position of Mars shown in this image, it hasn't even made a half circle yet. So put as simply as possible, Earth will make one full trip around the Sun faster than Mars will. Now look at position 1. You can see where Mars's position would be on the background stars. Now let's move on to position 2. And keep in mind, Earth's orbital speed is faster than Mars. So at position 2, when we look out at Mars, we would see it located here on the background stars. If you went outside on a nightly basis from position 3 to position 5, you would see something really strange happening. At position 3, you would see Mars located here on the background stars. But as we shift from position 3 to position 4, you would be seeing Mars moving back to the right. And then from positions 4 to 5, you would see Mars move even further back to the right. And then as we move on to positions 6 and 7, you would see Mars moving in its customary eastward direction. The final consideration in this vodcast is the birth of modern astronomy. And I'd like to focus specifically on Nicholas Copernicus. Now keep in mind that for almost 13 centuries after the Greeks proposed the geocentric model, it was the dominant model of explaining the solar system. And when things got really tricky was during the medieval times, because that's when the church formally adopted the geocentric model. From the church's perspective, it made complete sense to put Earth at the center of the universe because we were God's ultimate creation. That really complicated scientific progress. Because if you wanted to propose an alternative explanation for the arrangement of the solar system, you'd be risking death and exile, because this was the time of the Inquisition and the Crusades. And if the Catholic Church convicted you of heresy, your life would either be ruined or it'd be over. In fact, what's really interesting is Nicholas Copernicus waited until he was on his deathbed to share his sun-centered model for the solar system. But some of the key things that you should know about Nicholas Copernicus are that he concluded Earth was a planet. But what really defines Copernicus' contributions to science are that he was the first astronomer to propose a sun-centered universe. And in doing so, he ushered out old astronomy and facilitated the birth of new astronomy. I'd like to briefly call your attention to the picture you see on the right-hand side of this screen. Shown is the Copernican sun-centered model. The Sun is shown at the very center of our solar system, and then the planet Venus is between us and the Sun. But what's really important is, in the sun-centered model, Venus will orbit the Sun, and Earth will also orbit the Sun. And consequentially, all of the phases of Venus should be visible from Earth. Well, after the birth of modern astronomy and the scientific revolution, evidence overwhelmingly indicated that all of the phases of Venus are visible from Earth. So cheers to you, Nicholas Copernicus, and cheers to the birth of modern astronomy. Okay, that concludes this video podcast. In Vodcast 15.2, I will continue my discussion on the birth of modern astronomy, and in doing so, I will highlight the contributions of Johannes Kepler, Galileo Galilei, and Sir Isaac Newton.